Section 2.2 is an introduction to polynomials. Now, a polynomial is just going to be a finite sum of two different types of functions, constants, and the graph of a constant function is just a horizontal line, and power functions. So in this video, I'm going to go over power functions, what they are and what their graphs look like. And in particular, we're going to talk about the end behavior of the graphs. What happens when as x goes off to infinity or as x goes off to negative infinity, as you go really far to the left or to the right. Okay, so what is a power function? Well, it's going to be a function of the form f of x equals a times x to the n. So a here is my coefficient telling me how many copies of this power of x I have. We are going to put some restrictions on a and on n. For a, we're just going to require that that not be 0. So I've actually got to have some copies of x to the n. It could be a positive number, could be a negative number, but if I had 0, that would just kill this off entirely, and that would give me a constant function. Okay. For n, we're going to require that n be a positive integer. So it could be 1, 2, 3, 18, 205, okay. But it won't be a negative number. So we won't be seeing x to the negative 1, which would be the reciprocal function, or x to the negative 2, which would be the reciprocal of the squaring function. So we won't have any x's in denominators, okay? And we won't have fractional powers. So x to the 1/2 just means the square root of x. We're not going to have that. When we talk about a power function, we're only talking about positive integer powers of x. All right, and what I'm going to do is I'm going to just graph some of the power functions where the coefficient a is just 1, and then I know that multiplying by other numbers will stretch or shrink things vertically depending on the absolute value of a, and if a is negative, it would flip things upside down. Now, if I look at just x to the n, there are going to be two basic categories of this sort of power function. Again, where my coefficient is just 1. I'm going to have it if n is even, an even integer, and I'll have it if n is odd, an odd integer. I'm going to start with the even powers, and let's just see what those look like. Okay, so the first positive even integer that we have would be 2. So I could have f of x equals x squared. And we already know what that looks like. That's just our beautiful parabola that looks something like this. Okay, so I'm just going to write that as y equals x squared. That's the blue curve that we have there. Now, the next positive even power that we have would be the 4th power. So I can look at y equals x to the 4th. I'm going to draw that in purple. Now, there are a few points that are going to be on all of the graphs. The origin, 0, 0, will be on the graph of any power function, even or odd. But certainly here, because 0 to the 4th is 0. The point 1, 1 is on both of these graphs because 1 to any power is always going to be 1. And the point negative 1, 1 will be on both of these graphs because negative 1 to any even power is also going to be 1. And if I look at x to the 4th, the pattern's going to be very similar to the pattern that I have for x squared. If I look at just positive inputs, as x gets bigger, the 4th power of x also gets bigger. So I'm going to have a curve that increases and goes off to infinity. Okay. And I can see that the left side of the graph will be a mirror image. This is going to be symmetric about the y-axis, because if I were to replace x with negative x, I'd get exactly the same thing. Okay. So I'm going to have a very similar pattern. Now, it's tempting to think, oh, the fourth power is always going to be bigger than the second power. And most of the time it is. If I compare what happens at 2, for example, 2 squared would be 4, 2 to the fourth would be 16. So by the time we're at an x value of 2, x to the fourth is going to be much, much bigger than x squared. But if I look at fractional values between 0 and 1, there, the bigger power is actually going to give me the smaller number. If I take 1/2 and square it, 1/2 squared is 1/4. If I take 1/2 to the fourth power, that's going to give me 1/16, which is a lot smaller. So what's going to happen is between 0 and 1, the fourth power is actually smaller than the second power. So the graph of x to the fourth will be below the graph of x squared. At 1, they agree, and then for x values bigger than 1, the fourth power is going to be bigger. So if I look now, once I've passed 1, the purple graph is higher up than the blue graph. And then because we've got symmetry about the x-axis, we're going to have a mirror image over here. So it's steeper once we go past 1 on the right and -1 on the left, but it's actually less steep in between -1 and 1. Now, if I take a look at y equals x to the 6th, which is going to be the next even power that I have, I'm going to have the same basic idea here, okay? It's still going to be symmetric about the y-axis, because whether I plug in an even number, a positive number or a negative number, I'm going to get the same result. So even power functions are examples of even functions. Opposite input gives me the opposite output. Okay. These same 3 points, the origin, 1, 1, and -1, 1, are going to be on the graph. In fact, they'll be on the graph of any even power of x. Okay. And again, between 0 and 1, the bigger power is smaller. To the right of 1 and to the left of -1, the bigger power is bigger. So all my even powers, if I just have one copy of x to a positive even integer, I'm always going to get a U shape, something like so. Going to have these 3 points on the graph. The bigger the power, the less steep it is in this middle part, and the steeper it is on the ends. All right, so what can we say about functions that look like this? Well, first of all, they are even. So they are symmetric about the y-axis. In fact, I often remember the name even by saying an even function is just one that has the same sort of symmetry as an even power, like so. Okay. All right, so we'll have that. I want to talk now about the end behavior. The end behavior is just what happens when we go really far to the right and really far to the left. Now, if I look at what happens as I go really far to the right, it's going to be a while before I'm way over here. The graph's going to be really, really high up. But all of these arrows were pointing up and to the right. So as I go really far to the right, I'm just going really, really far up. Now, the way we indicate that is with some arrow notation. I can say as x goes to infinity, x to the n goes to infinity. Now, this is assuming that n is even. We're just talking about the even powers right now. I can't say x equals infinity because infinity isn't a number. But this just describes, we call it the end behavior, describes what happens as x gets really, really big. And I can then describe what happens on the left side. As x goes to negative infinity, x to the n will also go to infinity. Same result. That's because this is an even function, so opposite inputs give me the same output. Okay, excellent. So that's an understanding of our graphs of just these basic even power functions with a coefficient of 1. Now, if I had something like g of x equals negative 2 x to the 104th, okay, that's an even power of x. So I know the graph looks something like this U shape, but I've multiplied it by negative 2. The 2 stretches it vertically and just makes it even steeper than it would be. And then the negative flips it. So I could say as x goes to infinity, because we flipped it so that we're going to have more of an upside down U, as x goes to infinity, g of x would go to negative infinity. And as x goes to negative infinity, g of x would also go to negative infinity. So for power functions, if I know what the power does, then if I multiply it by a positive number, that function does the same thing. If I multiply it by a negative number, it simply does the opposite thing. Okay, so those are our even powers of x. We've been going for a little while in this video, so I think I'm going to do the odd powers in the next video. We'll pick up with that in a moment.